Now we're finally going to get to the punchline of why we spent so much time understanding the difference between conservative and non-conservative forces. Potential energy, for which we use the symbol U. All forms of potential energy, we're going to be using the symbol U. You can use the symbol PE, but most university textbooks will use U. So it turns out that only conservative forces are associated with potential energy functions. Potential energy function, you could just say equation if you want. But for example, only conservative forces are associated with potential energy functions like the force of gravity is a conservative force, so we have gravitational potential energy. The spring force is a conservative force, so we have spring potential energy, also called elastic potential energy. The electric force is a conservative force, so we have electric potential energy. And the relationship between the work done by the conservative force and the change in potential energy of an object is simply this. The change in potential energy, delta U, is the opposite of the work done by the conservative force. It's the opposite. Why? Why is this a negative sign? Why is that a negative sign? That of the, it's opposite of the work done. Well, here's why. If a conservative force does negative work now, it can pay us back with positive work later. It's like putting money in the bank. For example, let's say, here's my mass again. I am going to lift this up to here. Now my question to you is, how much work, or specifically what sign is the work that gravity did? I'll do it again. Lift it up. Now the force of gravity, I'm not asking about the work I did, I'm asking about the work of gravity, the conservative force. Gravity's pulling down this way, the displacement was up this way, so in other words, gravity's doing negative work. How much has the potential energy changed, the gravitational potential energy? Well, because it's the opposite of the work of gravity, I've got positive potential energy. That means that when I let this thing go, gravity will do positive work. I get paid back. Gravity does negative work. When I put it up to here, all I got to do is let this go, and gravity will do positive work on the way back. In summary, if a conservative force does negative work now, it'll pay us back with positive work later. Why is this a delta U? Why a delta U? And that's simply because potential energy depends completely on where you define potential energy equal to zero. One of the great things about potential energies, you can define zero anywhere you want, because the only thing that matters is the change. For example, if I define this level right here as zero potential energy, I lift it up, it's got positive, but if I drop it down, it's got negative potential energy. What the heck does that mean? All negative potential energy means, like it has right here, if I define this as zero height, negative potential energy means work's got to be done on the object to get it back to zero. So I've got to lift this up. I am exerting a force up. It's displacing up. I'm doing positive work to get it back up to zero height. That's all that negative potential energy means. Some outside force has got to do positive work to get it back up to zero. So let's take a couple examples here and talk about the potential energy functions of a couple of conservative forces we've already looked at. So gravity. The gravitational potential energy we define as mgh. This can be positive or negative, as that example just showed. Now, a better way to express this would be delta UG equals mg delta h, but because we can define zero wherever we want, it's okay to just do it this way as long as we've clearly established where we set zero. So this will be the height compared to where we set zero. Similarly, the work done by a spring, now this could be positive or negative over here, but here is why this is always going to be positive. If you set your x equal to 0 at the equilibrium position, then the work done, or the potential energy function of a spring will always be positive. Now you can set it somewhere else, but then you get these negative energies that can be very confusing. So my very strong recommendation is, when you're using springs, always set potential energy equal to 0 at the equilibrium position. In other words, where x is 0, where the string is unstretched, and then it will always be a positive potential energy function. It will always store positive energy. That's the easy way. Otherwise, you can get real confusing. So just set x equal to 0 as your 0 potential energy point, and then whether you stretch the spring or compress it, it will have positive potential energy compared to that 0 position.